Here N is total number of turns in the coil, I is current through the coil, A is area of coil, and B is strength of magnetic field. So from this you can write that your I is K theta over NAB. Now if I talk about a galvanometer, so in a galvanometer, this K, N, A, and B, these four terms are constant. Like torsional constant is a constant term, capital N, number of turns per unit length is a constant term, A, area of coil is a constant term, B, strength of magnetic field is constant. So this K by NAB is a constant which is sometimes represented by C and is known as galvanometer constant. This term is constant for a galvanometer and this is known as galvanometer constant. Remember this thing, galvanometer constant means K by NAB. Okay, after this we have few definitions related with galvanometer. The first definition is the definition of current sensitivity. Current sensitivity simply means, in a very simple language, current sensitivity means deflection in the galvanometer when you pass current of 1 ampere through it. I'm repeating again, current sensitivity means deflection in galvanometer when you pass a current of 1 ampere through it. So current sensitivity is deflection per unit current. Means when you pass unit current through the galvanometer, the deflection in the galvanometer is known as current sensitivity. We represent it by IS, and current sensitivity is simply deflection divided by current. So from this equation, if I calculate theta by I, then that theta by I is NAB by K. So this is your current sensitivity. Current sensitivity is NAB over K. We usually prefer a galvanometer having a high current sensitivity. Galvanometer with high current sensitivity are preferred. So we prefer galvanometer with a very high current sensitivity. From current sensitivity, you can get some conceptual questions. So if you can see that current sensitivity is directly proportional to number of turns. So the first question is, can we increase current sensitivity by increasing number of turns? Yes, they are directly proportional. If you can increase the number of turns of coil in your galvanometer, then your current sensitivity keep on increasing. But there is one limit. Because if you keep on increasing the number of turns, then size of the galvanometer will increase. Galvanometer have nothing but a coil. You have in a galvanometer, you have a core with number of turns of the coil. So the size of the galvanometer basically depends upon the number of turns and the area of the coil. If you increase the number of turns, then size of galvanometer will increase. And practically you can't have a very large galvanometer in your lab. So though IS is directly proportional to N, but N cannot be increased beyond a limit as it will make बल्कि होता चला जाएगा, साइज बढ़ता चला जाएगा आपके galvanometer का if IS is proportional to N. So Is is proportional to A, means if you keep on increasing the area of the coil, then also the current sensitivity will increase, but it's again, there's a limited, the same limit. You cannot increase the area of the coil to up to a certain limit, beyond a certain limit, because if you keep on increasing the area of the coil, then the area size of the coil will increase. You cannot increase it beyond a certain limit. Then this is directly proportional to the strength of magnetic field. Now, this is where you can increase the sensitivity. It is proportional to the strength of magnetic field. If you keep on increasing the strength of magnetic field, then current sensitivity will increase. To increase the strength of magnetic field, we use soft iron core. The property of soft iron core is soft iron core can increase the strength of magnetic field up to 1000 times. So to increase strength of magnetic field, soft iron core is used. Last, this is inversely proportional to K. So inversely proportional to K means to increase sensitivity, to have a very high sensitivity, you need a spring having very small value of K. So for which we usually prefer phosphorus bronze strip is used. So the spring of a moving coil galvanometer is made up of material which is an alloy of phosphorus and bronze, just to have a minimum value of K so that your current sensitivity is maximum. After current sensitivity, we have one more thing which is known as voltage sensitivity. There is one term which is known as voltage sensitivity. Voltage sensitivity means its deflection per unit voltage. Voltage sensitivity means its deflection per unit voltage. We represent voltage sensitivity as Vs. This is theta divided by V. So this is theta. We can write your V as IR. So that's voltage sensitivity, which is theta by IR. And what is theta by I here? Giovanna, what is theta by I? What is the value of theta by I? No, theta by I, it's current sensitivity. Yes, where R is resistance. Theta by I is current sensitivity, where an R is resistance. So that's voltage sensitivity, which is current sensitivity divided by the resistance. This is voltage sensitivity. Current sensitivity divided by the resistance of the coil. Okay. So as it depends on all those factors on which your current sensitivity depends. If your current sensitivity is NBA by K, there's just one R in denominator. So it depends on all factors on which your current sensitivity depends. But there is one small difference. See, if I increase number of turns, then current sensitivity increases, but not voltage sensitivity. On increasing number of turns, your voltage sensitivity will remain constant. See why it happens. On increasing number of turns, N, current sensitivity increases, but voltage sensitivity don't. So if I increase number of turns, then current sensitivity will increase, but not voltage sensitivity. Voltage sensitivity will remain constant. See why it happens. See, if I increase number of turns, if you remember, resistance is rho L by A. On increasing n number of turns, length of coil increases. Hence, resistance increases. If you increase the length of the coil, then resistance will increase. N by R will remain constant. So on increasing the number of turns in the coil, the length of the coil increases, resistance will increase, but N by R remains constant. So Vs does not change. Okay. So after voltage sensitivity, the next thing is why we don't use galvanometer to measure current. Why we only detect current using a galvanometer. Why we don't use galvanometer to measure voltage. Why we only detect voltage using a galvanometer. So galvanometer, I'm writing two notes. Galvanometer can't be used to measure current due to following two reasons. Due to following two reasons. The first reason is its resistance is quite large for the measurement of current. So if you try to measure current using a galvanometer, due to high resistance, it offers significant error. It have high resistance due to which it offer significant error in current measurement. Second. The second thing is that its range is very small. Like you cannot pass more than some few milliampere current through a galvanometer. Its current for full scale deflection is small. Usually in milliampere. Means through a galvanometer, you cannot measure current higher than few milliampere. The current that you can measure from a galvanometer is in milliampere only. If you try to pass more than few milliamperes current through galvanometer, then it can burn. It cannot withstand current more than 1 or 2 milliampere. So these are the two major reasons why we don't prefer galvanometer for measurement. We prefer galvanometer just for detection. The first thing is resistance is very high. So very high resistance. Due to that high resistance, it will offer error in the measurement of current. So for this thing, I'm giving this example. Say you have a resistance of 10 ohm. I connect this resistor to a cell of 10 volt. The current flowing through this is I. How much is I now? What's the value of I current? How much is I? Yes, 1. It's 10 by 10, it's 1 ampere. So current is 1 ampere. So 1 ampere of current is passing through it. Next, what you can do is to measure this current of 10 ampere, I connected a galvanometer. Let's say the galvanometer, the resistance of the galvanometer is 20 ohm. I connected a galvanometer of 20 ohm. Cell is 10 volt. How much is current now? What's the value of current now? See, current is V by R. So V is 10, but your R is 10 and 20 are in series. So it's 10 by 30, which is 1 by 3 ampere. So current is 1 by 3 ampere only. Is it clear? Your current is just 1 by 3 ampere, 0.33 ampere. So the actual value of current is 1 ampere. But if you are trying to measure this current using a galvanometer of 20 ampere, the value of current comes out to be 0.33 ampere. So there is an error of around 0.7 ampere. So that's why we do, see you're measuring current of 1 ampere. In 1 ampere, you're having error of 0.7. What you're getting is 0.3 only. The large error. So that's why we don't measure current using a galvanometer. The reason is resistance is very large. Resistance is 50 ohm, 60 ohm, sometimes 200 ohm. Due to that high resistance, we cannot use it to measure current. Okay. Okay. After current measurement, we can't even use it for voltage measurement. For current measurements, its resistance is large. But for voltage measurement, this resistance of 50, 100, 200 ohm is small. For voltage measurement, we usually prefer devices having very high resistance. Devices having very high resistance will have very small error. So for current measurement, this resistance is large, but for voltage measurement, this resistance is small. So for voltage measurement, its resistance is comparative small. Its resistance is small. Hence it offer error. Hence it offer error in voltage measurement. And the next thing, it's again the voltage for full scale deflection means it's full range. The maximum voltage that you can measure through this galvanometer is very small. That's known as voltage for full scale deflection is millivolt. So through this galvanometer, you cannot measure more than few millivolt. 1 millivolt is 10 raised to the power minus 3 volt. You cannot measure a voltage of 10 volt using a galvanometer. If you try to provide a very high voltage, then this gets burned out. This device will not work. This will get damaged if you provide a high voltage to this thing. So these are the reasons why we don't use galvanometer for the measurement of voltage. Okay. So now you know what is galvanometer, on what principle this galvanometer works, what is current sensitivity and voltage sensitivity, as well as you know that you cannot use a galvanometer for the measurement of voltage. You cannot use a galvanometer for the measurement of current. But what if you want to measure voltage? What if you want to measure current? Then you have to convert your galvanometer into other devices. So the first device is emitter. So conversion of galvanometer into ammeter and voltmeter. Into ammeter and voltmeter. So let's start with ammeter. So ammeter is simply a device which can measure current. This ammeter we obtain from galvanometer. So if you could remember why we don't use galvanometer to measure current, it's because of its high resistance and low range. So while converting galvanometer into ammeter, what we do, we first decrease the resistance of galvanometer. While decreasing the resistance, you will notice that range automatically increases. I'm repeating again. Why we don't use galvanometer for the measurement of current? The first reason is its resistance is large. The second reason is range is small. While converting galvanometer ammeter, we just decrease the resistance of galvanometer. While decreasing the resistance of galvanometer, the range of ammeter automatically increases. So you have this galvanometer G. I want to convert this galvanometer into an ammeter. So to convert this galvanometer into an ammeter, just connect a very small value resistance S in parallel with G. If you remember, in parallel combination we did, if I take two resistors in parallel, one of 10,000 ohm and another of 1 ohm. So if you take parallel combination, then the R equivalent will be less than 1 ohm. In parallel, the equivalent resistance is less than the minimum one. So if I take galvanometer and connect a shunt in parallel with the galvanometer, this S is small value shunt resistance. So when I connect this small value shunt resistance in the galvanometer, the resistance of galvanometer will decrease. Let's see some more parameters. Like the one parameter is IG. IG is current for full scale deflection. IG is current for full scale deflection for galvanometer. This is IG. After IG, we have one more term, which is I. I is range of ammeter. So this IG is the maximum current that you can pass through your galvanometer. This is usually in milliampere. Where I is the range of your ammeter. The current that you want to measure from your ammeter is range of ammeter. So I give you a galvanometer. I ask you to measure 10 ampere current through it. So that 10 ampere is the range. So the current that is passing through the galvanometer is I current. Out of this I current, only Ig can pass through galvanometer. If you pass current more than Ig through the galvanometer, then it can get damage. So out of I, Ig will pass through the galvanometer and we are left with I minus Ig. The rest I minus Ig will pass through the shunt and this will be I. This whole system, shunt with galvanometer with this shunt resistance, is basically your emitter. So just by connecting a low value shunt resistance in parallel with the galvanometer, its overall resistance decreases as well as its range increases. Earlier, it can measure only Ig current, but now you can pass your current I more than Ig through it. Now, the next task is to calculate this shunt resistance. You want to calculate the value of this shunt resistance. Yeah. So I is the range. The total current that we are passing through this galvanometer is I. Out of I, Ig is passing through the galvanometer. So out of I, if Ig pass through galvanometer, then we are left with I minus Ig. That I minus Ig will pass through this shunt. I minus Ig will pass through shunt. This is the current that is passing through the shunt. Okay, Joanna? Now, since S and G are in parallel, okay, do you remember if two resistors are in parallel, then out of current and voltage, which quantity will be same? If two quantities are in parallel, that means then out of current and voltage, which quantity is same? Yes, Joanna is correct. What about Johanna? Yeah, Fatima is correct. Johanna, if two resistors are connected in parallel, then out of current and voltage, which quantity will remain same? Voltage remains same. In parallel, voltage remains same. Voltage across shunt is equal to voltage across galvanometer. So what's the voltage across the shunt resistance? The voltage across the shunt resistance is this resistance multiplied by current. It's I minus Ig into S. And what is the voltage across the galvanometer? The resistance of galvanometer is G. G is resistance of galvanometer. It's Ig into G. The current through the galvanometer is Ig. Resistance of the galvanometer is G, not R. It's Ig into G. G means resistance of galvanometer. This is resistance is G. Through this current Ig is passing. So voltage is Ig into G. So shunt resistance is G into G by I minus Ig. So the value of shunt resistance is it's IgG divided by I minus Ig. This is the shunt resistance. So if you can see, shunt resistance is inversely proportional to the range. So if you keep on increasing the range of the emitter, then the value of shunt resistance will keep on decreasing. It's inversely proportional to the range of the emitter. In the next thing, see here, galvanometer and shunt resistance are connected in parallel. So you can calculate equivalent resistance. Shunt resistance and galvanometer are connected in parallel. So the equivalent resistance of the system is, if two resistors are connected in parallel, or instead of equivalent resistance, I should write that resistance of ammeter. Okay, can you tell me how much is the resistance of ammeter? Just parallel of S and G. G into S by G plus S. If you can remember, in parallel combination of two resistors, we can use this shortcut, na, R1 R2 by R1 plus R2. So that's G into S by G plus S. That's the resistance of ammeter. So okay, tell me, which ammeter will you prefer? An ammeter having a high resistance or ammeter having a low resistance? Which ammeter would you prefer? An emitter having a high resistance or emitter having a low resistance? So emitter having a minimum resistance will have minimum error. So if I say that I need an ideal emitter, resistance of an ideal emitter is 0. So it's best if it doesn't have any resistance. So if you're saying that your emitter is ideal emitter means your emitter does not have any resistance. It will not offer any error. So that's ideal emitter. Resistance of an ideal emitter is 0. See, this is your given circuit. Zero point 0.02 ohm. So that's the value of your shunt resistance. C is an ideal emitter. So this is the circuit. You want to measure the current through this resistance. To measure this current, you are using this emitter A. In the first part, that emitter is basically a galvanometer. So can you guess the value of current through the circuit if this is a galvanometer having a resistance of 60 ohm? See, if you want to measure current is total EMF by total resistance, right? So it will be R. If I call this as R, it's R plus G. So that's 3 by 3 plus 60. So it's 3 by 63. So which is 1 by 21 ampere. So both Fatima and Johanna were correct. No, Johanna was not correct. Why 1 by 12? Fatima was correct. Is it clear? Johanna and Johanna? Okay. So that's the first part. Oh, it's part A. Part B, you are measuring current not through galvanometer but through an ammeter. And for making ammeter, you are using a shunt resistance of 0.02. Now, can you guess the value of current? See, if you say that this is an ammeter, then you need resistance of ammeter. The resistance of ammeter is simply G into S by G plus S. Just keep on substituting the values. G is 60. S is 0.02. It's 60 plus 0.02. The resistance of ammeter is 60 into 0.02. So that will be 12. 60 into 2 is 120. It's 1.2 by 60.02. So that's the resistance of ammeter. And the current in the circuit is EMF. So now you have this resistor R and an emitter of resistance RA. So it's R plus RA. So it's 3 by 3 plus 1.2 by 60.02 ampere. Okay, now tell me the answer of third part. Third part is trivial. Easy calculation, straightforward numerical. Answer of third part I need. No, Jubaina, I need reading of emitter. Will it read 0? Jubaina, just check what is 0 in an ideal emitter. What is 0? Is it current is 0 or its resistance is 0? Resistance is 0. I'm asking current. It's E by R plus RA. So E is 3, your R is 3, your RA is 0, it's 3 by 3, which is 1 ampere. So this is the current, which is 1 ampere. Okay, solve this one. A galvanometer. See, your G is 12 ohm. Fatma, what's your answer? IG is 2.5 milliampere. Means 2.5 into 10 raised to the power minus 3 ampere. That's your IG. Current for full scale deflection. The range of the emitter is this 7.5 ampere. You can write the expression for your shunt resistance as it's Ig into G over I minus Ig. So your shunt resistance is it's 2.5 into 10 raised to the power minus 3 into G, which is 12, by I minus Ig, it's 7.5 minus it's 2.5 into 10 raised power minus 3. So this is the value of shunt resistance. It comes out to be I have to use calculator. Huh? So that's 12 into 2.5, which is 24 or 6, 30. It should be 30. Let's solve it. So this is basically 2.5 into 12, 30. So it's 30 into 10 raised to the power minus 3. 7.5 minus 2.5 into 10 raised per minus 3. So that means 7.5 minus 0.0025. So it's 30 into 10 raised power minus 3 by 7.5 minus 0.00, no, 00. 7.5 minus, so it comes out to be 7.49. So your shunt resistance is it's 30 divided by 7.49. So it comes out to be 4 into 10 raised to the power minus 3. So to convert this emitter into this galvanometer into an emitter, you need to connect a shunt resistance of this value. We can as well calculate the emitter resistance. The resistance of emitter is GS by G plus S. Although it didn't ask in question to calculate the resistance of emitter, if it asks, then you can calculate resistance of emitter as GS over G plus S. Conversion of galvanometer into voltmeter. So what were the two issues with galvanometer due to which you cannot use it as a voltage measuring device? The first issue was its resistance was small or large? Resistance was small. For measuring voltage, its resistance was small. Just check. Its resistance was not large, its resistance was small. You need large resistance to measure voltage. And the second is its range is small. So just like last case, we will try to increase resistance. See, in emitter, we will trying to decrease the resistance of galvanometer. But to convert galvanometer into a voltmeter, we will try to increase its resistance. Now, can you guess how would you increase resistance? By connecting another resistance in parallel or by connecting a resistance in series? Hmm. Yes, yes, you're right. Everyone is right. For conversion, we connect a high value resistance, in series. For this conversion, we will connect a very high value resistance in series with the galvanometer. So this is the galvanometer. In series with the galvanometer, I connected a high value resistance. I connected this resistance in series. So current through this is Ig. Some voltage Vg drop across G. See, if I take case when only the galvanometer, you have only galvanometer, no resistance, then the current passing through the galvanometer is Ig. Its resistance is G, so the voltage drop across the galvanometer is Vg. Vg we call voltage for full scale deflection. Vg is voltage for full scale deflection. Voltage for full scale deflection means the maximum voltage that you can measure using this galvanometer. The maximum voltage that one can measure through this galvanometer is Vg. It's voltage for full scale deflection. This Vg I can write as it's Ig into G. That's the maximum voltage that can be measured. But I want to measure a voltage V which is higher than Vg. So now I have two tasks. The first task is to increase resistance. The second task is to increase range. You will see when we increase resistance, range will automatically increase. See, if you just have galvanometer, then it can measure only up to Vg. But along with galvanometer, if I connect a resistance R in series, say G and R both are in series, so current through R will be Ig. Voltage across R is IGR. You can see this very clear that earlier the voltage across the system is just Ig. But now along with Ig, you can measure IGR. So this whole thing is known as voltmeter. And this voltmeter can measure voltage which is greater than Vg. This whole voltage Vg plus IGR is known as V. This is the range basically. So you can write that range of voltmeter V is its Vg means voltage across the galvanometer plus voltage across this resistor R in series, it's IGR. Is it clear? This is statement. Because after this statement, there are only mathematical steps. This is the concept. The entire concept is in this equation. Is this concept clear that after connecting this series resistance, the total voltage that I am measuring is voltage across galvanometer as well as voltage across the resistor. So in short, your range have increased by connecting resistance R in series. So everyone agree that this is correct. Is it clear up to this point? Sure. Next, I call this as equation number 2. Next, what we can do, we can substitute the value of Vg from 1 and 2. So if I substitute 1 and 2, then I can write that Vg is Ig into G plus Ig into R. See here, I'm interested in this R. We need a relation between the resistance R that you will connect it in series and the range of the voltmeter. So for this R, you can do one thing. You can take this Ig as common. It's G plus R. It's V by Ig, which is equal to G plus R. Next, you can calculate R, which is V by Ig minus. So this is the value of resistance R connected in series. That's V by Ig minus. So as you can see that R is directly proportional to range. So higher the range of the voltmeter, higher would be the value of resistance that you will connect in series. Okay, now can you tell me the resistance of voltmeter? What's the value of resistance of voltmeter? How much is the resistance of voltmeter in terms of G and S? Tell me. How much is the resistance of voltmeter in terms of G and R? So it's simple. G and R are connected in series. So how much is RV? This is simply the series combination of G and R. G and R are connected in series. So the resistance of voltmeter is just the series combination of G and R, G plus R only. So that is your RV. Okay, now what type of voltmeter would you prefer? Voltmeter having low resistance or voltmeter having high resistance to minimize the error? High resistance. So if I say that I'm making an ideal voltmeter, so what should be the resistance of an ideal voltmeter? So what do you think? What should be the resistance for an ideal voltmeter? Yeah. And that maximum value is infinite. So if you have an ideal voltmeter, its resistance is absolutely infinite. It will not withdraw any current from the circuit. So it will not offer any error in the flow of current. So this is how we can convert your galvanometer into emitter. The question is, a galvanometer see the resistance is it's V by Ig minus G, right? So if I substitute values, V is 8. How much is Ig? It's 1 milliampere. Don't forget to convert this milliampere into ampere. It's 1 milliampere means 10 raised to the power minus 3 ampere. It's 10 raised to the power minus 3 minus G, which is 20. So your R comes out to be 8,000 minus 20. 8,000 minus 20 means 7,980. That's the resistance. The resistance that you will connect in series. And the resistance of voltmeter, it's simply this resistance plus the resistance of galvanometer. This is the resistance of voltmeter. So you can say that resistance of voltmeter is 7980 plus G, which is 20. So it comes out to be 8,000 ohm. That is the resistance of your voltmeter.